This video is mainly for second period because we didn't have as much time today, but everybody's free to look at it. What we did do in second period was we did this very simple exercise where we started with an extremely simple sequence and we did partial summing or running totals over and over again. And what we discovered is we saw Pascal's triangles come out of that. Now, it wasn't in this visual format, but what it was is actually the original, or well, not the original, but one of the ways that Pascal wrote it down. It's a little hard to read this picture, but you can see this is in a more rectangular grid, and then 2, 3, 4, 5, 6, 7, 8, 9, and then and you can see the pattern. Well, it's really hard to read the numeral exactly, and you have to see the presentation of Pascal's triangle. We mentioned the standard rule for creating Pascal's triangle, which is that any entry such as this 10 is the 4 plus the 6. Well, how does that correspond to what we were doing? So for example here, this 6 was the 3 plus the 3, this 4 is 3 plus 1. I think is a nice little animation of how it works. Well, that's working because, for example, if we're doing the running totals of the ones, suppose we had summed up these 3 ones to get 3, and then we want to get the next thing, the running total. Well, we're going to be summing up. You could do it two ways. The inefficient way to go back to scratch and add up these 4 ones to get a 4 in this entry. But the efficient way is to take the 3, which is the running total you already have, and just add one more. And so if these are the running totals of these guys, then adding one more is just going to bring in this entry. So for example, the 6, that's the running total of 1, 2, 3. Oop, it disappeared. Let's get back up here. The 6 here is the running total of 1, 2, 3, which is the 6, and then add the 4, you get 10, which is the running total of 1, 2, 3, and 4. So it's just an alternate way of expressing that basic rule for Pascal's triangle. But I want to now talk about a seemingly completely different place where this Pascal pattern comes up. And the point here I want to get across is that this Pascal pattern just shows up so many places. We will see it in at least 3 or 4 different places, and it shows up in many other places as well. And so what we're going to do, and this is something that's hopefully review, is just look at x plus y to various powers. X plus y to the 0 is pretty boring. It's just 1. X plus y to the 1 is just x plus y. And I'm going to emphasize the coefficients there. It's 1x plus 1y. X plus y squared is x squared. That's 1x squared. Plus, and then when you multiply the xy and the yx, they combine to be a 2xy plus y squared. Now let's look at x plus y cubed. Let's try and do this in a smart way. And in fact, doing it in a smart way not only will save us work and be lazy like we always want to be, but it'll show us a pattern that's going to be able to be used. That's x plus y times x plus y squared. We don't want to multiply it all out again when we could use previous work. Okay, so that is that 1x squared plus 2xy plus 1y squared. And now what are we going to get? Well, we're going to get, let's expand it out. We're going to get x, we'll get 1x cubed plus, now how many, we're going to get some x squared y's in here. We're going to get x times xy, so we're going to get a 2 times x squared y. But that's not the only place x squared y could come from. It could also come from this x squared plus this times this y. So 2 plus 1. Plus, now what else could we get? We could get 1x and 2 y's. And what's going to go in front of that? Ooh, not that. That's going to have the 1 from xy squared and the 2 from y times xy. Okay, 1 plus 2. And then the last thing we can get is a y cubed. And that's just one way to get that. Okay. So that's going to be x cubed plus 3x squared y plus 3xy squared plus 1y cubed. I'll put the 1 in front of the x. Well, that's 1, 3, 3, 1. 1, 1, 1, 1, 2, 1. Whoops. 1, 3, 3, 1. Is it a coincidence that's Pascal's triangle? Well, let's see. Where did this 3 come from, for example? It came from a 2 and a 1. And which ones were they? The 2 was this 2, of course. And the 1 was this 1. And so the 1 and the 2 that's on, if you look at the triangle pattern, it's on the left-hand side in the middle of the 1, 2, 1 row. Those added up to be the second entry in the 1, 3, 3, 1 row. Let's look at the triangle again. The 1 and the 2 add to be a 3. So the fact that when you take the x plus y and you multiply it in, there's going to be 2 ways to get all these internal entries. That's going to correspond to the Pascal rule. Let's do it one more time. And that's going to be x plus y times this whole thing. And that's going to be, well, let's see, x times the x cubed is going to be 1x to the 4th plus, let's go ahead and do x cubed y. That's going to be, well, there's one way to do that from there, 1x cubed y, plus the other way is take an x and times the x squared y. And that's going to be 3. There's no other way to do it, because I can't take an xy squared and multiply by either x or y and get an x cubed out of there. It's just not enough. The only way things it can come from are the one that already had the full x cubed in it and just needs the y, or has x squared and y and just needs another x. Then the second thing is going to be, the third term rather, is going to be x squared y squared. Let's do it in decreasing order of x. It's very important to do this systematically, or else you're going to get very confused. But a very standard way to do it is always order these in the decreasing order of the x powers, and therefore increasing order of the y powers. Notice that all the powers sum to 3. This is like a y to the 1. That's an x to the 1. There's no way you're going to get anything where the powers don't sum to 3. Because every time we're multiplying either an x or a y, and we're multiplying them 3 times. And so there's no way you could get like just an x squared alone. Now here, x squared y squared, that could be an x times 3x squared y squared, so that's going to be 3. Or a y times 3x squared y. Aha, 3 plus 3, and that's going to be 6. And then plus 3 plus 1, very similar, x y cubed plus 1 y to the 4th. And of course, that's giving us 1x to the 4th plus 4x cubed y, plus 6x squared y squared plus 4x y cubed plus 1 y to the 4th. And that's the coefficients there of the 4th row of Pascal's triangle. So let me take a break from the developing the theory for just an example. Suppose somebody wanted actually to expand something out a little more complicated, like 2x plus 5y to the 4th. Would I have to redo this? Well, no, because that's, let me just put it in parentheses, that's something plus something else all to the 4th power. And the beauty of algebra, as always, the most important thing about algebra is that x and y here can be anything. They don't have to be single letters. So I can treat 2x as the quantity that's represented by x here, and 5y as the quantity that's represented by y here. If I wanted to make that a little more formal, I could use different letters. And just say, okay, I'm going to use the version of Pascal's triangle where I use u and v as the letters. And that's going to be, you don't have to do it with this level of formality, but it shows the idea a little more clearly, perhaps. It doesn't matter what the letters are, so this is certainly going to be true. But then I can just substitute in what u is. That's 2x. So that's 2x all to the 4th plus 4 times the quantity 2x cubed times the quantity 5y plus 6 times the quantity 2x squared times the quantity 5y squared plus 4 times the quantity 2x times the quantity 5y cubed plus the quantity 5y to the 4th. And then when we expand that out, it's going to look totally different. It's going to be 16x to the fourth. Those coefficients, that beautiful 1, 4, 6, 4, 1 pattern, is going to go away. And you might think, oh, that can't be coming from the binomial theorem. Well, it does. It's just the mixture of the 1, 4, 1. Let me put the 1 back in. The 1, 4, 6, 4, 1 pattern with the powers of 2 and 5 that come in here. And so that's going to be, let's see, 4 times 5 is 20, times 8 is 160, x cubed y, plus 6 times 20, let's see, actually that's a 2 times 2 times 5 times 5 is just 100, so that's 600, x squared y squared, and then 2 times 5 is 10, 4 times the 25, so that's 1,000, I think, xy cubed, and then plus 5 to the fourth is 625. It's 25 squared. So there's some weird numbers, but that's because it's a mixture of the Pascal pattern and the powers of 2 and 5. Another example of how that gets even more weird looking would be if you had like x squared y plus 2y cubed, all cubed. Then we can do the same thing. Let me do it without the u and v this time. It's just going to be whatever you see first, the first part of the binomial cubed, plus 3 times whatever that was, squared, times whatever the second thing was, not squared, plus 3 times x squared y times 2y cubed, squared, plus the 2y cubed, all cubed. And then you just expand it out. That's x to the 6y cubed plus 6x to the fourth y to the fifth, oops, to the fifth, plus 12x squared y to the seventh plus 8y to the ninth. So if somebody just told you this string, this polynomial, you'd be maybe a little bit bewildered as to how that could have come from a Pascal pattern of 1, 3, 3, 1. And the coefficient, the powers don't even look right, but that's because we had these weird powers to start with. Okay, actually let me split this into 2 videos, so let me stop there and then continue with another perspective on Pascal in just a minute.